Hello, science enthusiasts, and welcome back to the channel. Today we're diving deep into one of the most fascinating and, let's be honest, mind-bending topics in all of physics, Einstein's general theory of relativity. Now, I know what you might be thinking. Isn't that the super complex theory with all the crazy math? Well, yes. But what if I told you there's a new, more intuitive way to visualize it? A way that moves beyond the classic bowling ball on a trampoline analogy and gives us a richer, more accurate picture of how our universe truly works. For over a century, the standard way we've been taught to picture gravity is this. Imagine a stretched rubber sheet. If you place a heavy object, like a bowling ball, in the center, it creates a dip, a curve. Then, if you roll a smaller marble nearby, it doesn't get pulled by the bowling ball directly. Instead, it follows the curve in the sheet. This is a brilliant starting point. It beautifully illustrates the core concept that mass tells spacetime how to curve, and spacetime tells mass how to move. It's a powerful metaphor that has helped generations of students grasp this revolutionary idea. But, like any analogy, it has its limits. A big one is that it's a 2D representation of a 4D reality. Our universe isn't a flat sheet. It has 3 dimensions of space: up, down, left, right, forward, backward, plus 1 dimension of time. The rubber sheet model flattens all of that, which can lead to some confusion. For example, it makes it look like gravity is an external force, pulling things down into the curve, which is exactly the old Newtonian idea Einstein was trying to replace. Gravity isn't a force pulling from another dimension. Asterisk is asterisk the curvature of spacetime itself. Another issue is how it handles time. In general relativity, gravity doesn't just warp space, it warps time too. It's called gravitational time dilation. Clocks tick slower in stronger gravitational fields. A clock at sea level will literally run a tiny bit slower than a clock on top of a mountain. This effect is real, measurable, and crucial for technologies like GPS to work correctly. The rubber sheet model doesn't really have a good way to show this warping of time. It's all about the spatial curve. So how can we do better? Let's try a different approach. Forget the rubber sheet for a moment, and let's focus on the paths that objects take through spacetime. These paths are called geodesics. In flat, empty space, a geodesic is just a straight line. An object in motion will stay in motion in a straight line forever, just as Newton said. Simple enough. Now let's introduce a massive object like our sun. According to Einstein, the sun doesn't create a dip in a sheet. Instead, it warps the very fabric of spacetime asterisk around asterisk it. The key insight is this. Objects like Earth are still trying to travel in the straightest possible line through this warped spacetime. But a straight line in curved spacetime looks like a curved path to us in our 3D view. Imagine an ant walking on the surface of an orange. The ant thinks it's walking in a perfectly straight line. It never turns left or right. But because the surface of the orange is curved, if the ant walks long enough, its path will curve around the orange. From our higher dimensional perspective, we see its path as a circle. But from the ants to D perspective, it's following a local straight line. This is exactly what's happening with Earth and the Sun. Earth is simply moving along its geodesics, version of a straight line through the spacetime that has been curved by the Sun's mass. The force of gravity we feel is just us experiencing this geometry. It's not a pull. It's a push from spacetime itself, directing us along these curved paths. So let's build our new visualization. Instead of a rubber sheet, picture a 3D grid, like a lattice filling all of space. This represents our 3 spatial dimensions. Now, imagine a massive object like the sun is placed in the center. The presence of this mass doesn't create a funnel. Instead, it causes the grid lines near it to be squeezed together. The space itself becomes denser, more compressed around the mass. The more massive the object, the more it squeezes the grid. If you were to measure a 1 meter distance far away from the sun, and then measure a 1 meter distance close to the sun, the ruler itself would be in a more compressed region of space. Your path through that space is affected. A straight line path now has to navigate this squeezed grid, causing its trajectory to bend. This is a much more accurate way to visualize the warping of space. But what about time? This is where it gets really cool. We need to add the 4th dimension. Let's imagine that at every single intersection point on our 3D grid, there's a tiny ticking clock. In empty, flat spacetime, all these clocks are perfectly synchronized, and tick at the exact same rate. Let's bring our sun back into the picture. We already know it squeezes the spatial grid, but it also affects the clocks. The clocks closer to the sun, where gravity is stronger, start ticking more slowly than the clocks farther away. So now we have a complete picture. Near a massive object, the grid of space is compressed, and the rate of time is slowed down. This combined effect is the curvature of spacetime. Let's see how this explains in orbit. Imagine Earth moving through this grid. Far from the sun, it's moving in a straight line at a constant speed, passing synchronized clocks at a steady rate. As it gets closer to the sun's influence, it enters the region where the grid is squeezed, and the clocks are slower, because the space on the inside of the orbit closer to the sun is more compressed and the time is slower than on the outside of the orbit. The Earth's path is naturally nudged. It's constantly trying to move straight. But the geometry of space-time itself, the different rates of time, and the compression of space on one side, versus the other forces its path to curve. It's like a car with one wheel turning slightly slower than the other. It will naturally turn. Earth isn't being pulled. It's following the path of least resistance through this complex four-dimensional landscape. This is its geodesic. This grid and clocks model helps us visualize other phenomena too, like gravitational lensing. When light from a distant galaxy passes by a massive object, it's not being bent by a force. It's following a straight line, a geodesic, through the curved spacetime. Because the space is compressed around the massive object, the path of the light ray appears bent to us, creating multiple images or arcs of the distant galaxy. Our model shows this perfectly. The light ray follows the squeezed grid lines. This way of thinking gets us closer to the mathematical reality of general relativity. It avoids the misleading downward pull of the rubber sheet and explicitly includes the crucial role of time dilation. It shows that gravity is a property of the geometry of the universe itself, a beautiful and intricate dance between matter, energy, space, and time. So the next time you think about gravity, try to replace the image of a bowling ball on a trampoline with this new picture. A vast dynamic grid of space filled with clocks ticking at different rates, all being warped and shaped by the presence of mass and energy. Objects aren't being pulled. They're simply navigating the straightest possible paths through a beautifully curved universe. It's a more complex image for sure, but it's also a more accurate and powerful one. It helps us understand that we are living inside the geometry, not just observing it from the outside. Thank you so much for joining me on this journey through space-time. I hope this new visualization helps you appreciate the elegance of Einstein's theory in a new light. If you found this helpful, or have your own ways of picturing these concepts, please share them in the comments below. I love reading your thoughts. And if you want to explore more big ideas in science, don't forget to like this video and subscribe to the channel. It really helps us out. Till next time, stay curious.